SungHyoun Song presents Deep Dive into ART, Android RunTime for Dynamic Binary Analysis. This talk proposes a new technique to quickly and effectively analyze the app by modifying the ART. It shows an environment in which an attacker can steal code, interface, parameters, return value, fields, and stack trace of a function executed with using a debugger of soothing tools in real time.
Hi, nice to meet you everyone. My name is SungHyoun Song. I work at FSI of South Korea. The FSI is responsible for the security of Korean financial security, and I am research mobile security at FSI, and I do penetration testing for Korean company. I have experience speaking at several international security conferences in Europe and Asia. Today, I'd like to analyze how Android runtime works in detail, and based on the analysis result, I'm going to propose a technique to analyze the app easily and effectively by customizing the Android runtime. First of all, I want to explain why I became interested in the Android runtime. Analyzing mobile app is very important process for those who work in mobile security, like malware analysts or hackers. This is because it's possible to get a clear idea of how malware works or find vulnerability in your mobile apps only when proper analysis is done beforehand. There are two main ways to analyze the mobile app. First, you can analyze the app if it exists as a file. In general, in Android, bytecode can be converted back to the original Java source code using open source tools such as debugger. Another way is to analyze the app while the file is executed and loaded in memory. There is a dynamic analysis tool called Frida that can analyze the app during the runtime. Frida is a very high-level framework, and it's used by almost all security researchers today. So applications that handle sensitive information, such as banking, gaming, and healthcare, adopt the security technique to protect themselves from the analysis and attack. We call this technique RASP, Runtime Application Self-Protection. Many security companies develop RASP, make it as a module, and sell it. And most of apps with sensitive information are actually using the module. This technique checks not only whether the OS has been tampered, but they also encrypt, transmit, or receive data. In addition to that, they detect and block the attacker from accessing the memory area. So if you try to analyze an app protected by RASP, you will be detected and blocked as shown in the picture here. This top picture shows the process of decompiling to original Java source code using debugger. Since the app is protected by anti-decompile technique, you are in trouble with converting it back to the original Java source code. The bottom picture here shows warning message generated when it detects app running in a root environment or any attempted dynamic analysis using Frida. So can we bypass RASP? Of course. In my thought, there does not exist 100% of security, but what I want is automated and effective and fast method. However, security modules are difficult to bypass because they are applied in multi-ways technique. So what's the problem? The problem is time. They also know that the RASP cannot defend completely the attacker. The purpose of the RASP is to annoy the attacker as much as possible and increase the time required for the attack. There is no perfect mechanism, and we are instead continue have to fight. I want to get away from the endless fight between protection and bypass, just like Tom and Jerry. So over the past few years, I have been thinking about how to analyze the app easily and effectively without being detected by RASP. Then I found two papers published in Unix 2010 and AMC 2016. The main subject of paper were about developing a framework that can dynamically analyze app by modifying the runtime of Android. It was very interesting as it modified the OS to create the environment for analysis. But the advantage of technique was that app could not be analyzed without direct access to the app's executable file or memory. But unfortunately, the paper were written for all the Androids. So I had to analyze the new runtime in Android 10 in detail. So I shift my focus from application to Android OS itself, and that is kernel and platform. In the past few years, I started to analyze the Android source code and develop the custom OS. So I ended up building an Android OS by customizing the kernel and platform. The OS has built-in functions such as backdoor for privilege escalation, SE Linux bypass, safety net bypass, Android verify boot bypass, and kernel memory access driver. I don't think I can cover all of these today due to the limit time. So in this session, I will focus on presenting how customize the runtime for the dynamic analysis of application. ART is abbreviation for Android runtime. ART can be called the heart of Android and play a key role in loading app binary, application memory management, app execution, and optimization. However, it is not easy to analyze in depth how the runtime works in the restless version of Android. This is because the size of code is huge, about 150 gigabyte, and various techniques compiling, profiling, and optimization are also applied to the REST version of ART. In addition, since Google has changed the Android runtime drastically each time a new version of Android is released to optimize the performance, storage usage, and the system update of apps. How it's structured and how it operates are different from each runtime version. However, since all bytecode of app is interpreted and executed through the ART, if the attacker understands how exactly the app works on ART, all necessary information can be stored in real time to analyze the app. In this speaking, therefore, aim to analyze Android 10 ART in detail, I propose a new technique to quickly and effectively analyze the app by modifying the ART to deviate from the existing app analysis method. This technique is not detected by RASP and enables dynamic analysis of all the functions executed through the ART. And I also develop a framework in which an attacker can steal code, interface, parameters, return value, field, and stack trace of running function in the real time without using debugger or hooking tool. Let's take a look at how Android runtime has changed from version to version. First, when we talk about Java and Java Virtual Machine, An Android application written in Java language for developer productivity and code mobility. On desktop and server environment, a Java program is compiled to the Java bytecode, which is an intermediate representation for Java virtual machine. Java virtual machine run the Java bytecode. The Java bytecode is based on the stack-based instruction. However, since the performance of stack-based Java bytecode on resource-limited mobile device is poor due to slow interpretation, so Android researchers have created a new bytecode set, which is an Dalvik bytecode for Dalvik virtual machine, to improve the performance of Android application. In contrast to Java bytecode, the Dalvik bytecode is based on register-based instruction set. Therefore, it can reduce the code size and the running time in mobile device. Until Android Proio and earlier, there was only interpreter in Dalvik virtual machine. Every time you run the app, the interpreter converts all bytecode into native code. It slows down apps startup time so badly. In order to boost up the performance, just-in-time compiler was introduced in Android Proio on Dalvik virtual machine. Just-in-time compiler cache the code while generating the native code at the time of execution to prevent the repeated generated of native code for each time of same function call. As frequently used functions are executed with the native code that was created in advance, the performance has increased. These codes, however, consume amount of memory. The runtime structure where JIT and interpreter were in place had not changed for a while. The conventional approach results in very low performance when compared to the compiled language like C and C++. As a result, slow and space-constrained computing devices have tended not to include the virtual machine. So in Android Kitkat, Google introduced a new runtime, ART. In Android Kitkat, ART was experimentally available. Starting from Android Lollipop in 2015, Google decided to replace Dalvik virtual machine and made ART as a default runtime to improve the runtime performance. ART adopted ahead of time compilation strategy instead of interpretation. ART provides a compiler called DEX2OAT. The DEX2OAT will directly compile DEX bytecode into native code during the app installation and then stored as an AOT file. The result is essentially an ERF file that is then executed natively. So instead of having bytecode that is interpreted by virtual machine, it has native code that can be executed natively by the processor. This is called the AOT compilation. But main difference is that ART precompile everything, but Dalvik virtual machine use heuristic to detect the code that run most often and only compile a subset of bytecode during the execution. And another difference between the old Dalvik virtual machine and ART was the performance. As all the execution code of app were ran as native code, the startup speed was improved compared to the bytecode. In addition to that, every time you ran the app, it didn't use the interpreter, but it called the native code, and it resulted in reducing battery consumption. Since JIT wasn't used anymore, the memory usage was also reduced because it didn't keep the code cache in memory. And of the Aot compilation, the DEX2 OAT compiler can perform multiple passes for optimization to achieve better performance. But it lost as much as it gained. The biggest problem was it took too much time to install app, and it took too much time to update the system via OTA. Eventually, by compiling all bytecode to native code at app install time, it gained the app's performance. However, it required much more time to update app and system and more storage too. Then, is it really the best compile all bytecode into native code at app install time? We needed to first understand the usage pattern of a mobile user. In fact, we don't use all of the menu in the app. For example, I use a mobile banking app. There are a lot of financial related menu in the app, and I use just two. First, I check how much is in my account. Second, I transfer money from the account. That's it. Although there are so many menu in the app, I use only two features. Then you don't really need to compile everything, wasting your time and storage. All you need is to selectively compile the code that are frequently used by the user. So in Android 7, Google was reintroduced the just-in-time compiler that was removed in Android 5. The just-in-time compiler complements Aot compiler and help improve runtime performance. And they removed the bytecode compiling step in Aot compilation during the app installation. So when will the Aot compiler start working? Google introduced a new technique called profile guide optimization. During the app installation, the Aot compiler does not operate, and the app is not installed immediately as bytecode. When you use the app, the bytecode is executed using the interpreter, and it counts how many times each individual function is called at execution time. As the number of execution increase, it divides the state of function from cold to warm and finally hot. Once the state of function becomes warm, the profiling info is created to record the information such as the number of execution, then save in the mobile device. When you don't use your phone or when you charge it, based on the profiling info, the profile service use Aot to compile the bytecode into native code and store it. And once the state of the function reaches hot, the bytecode is compiled into the native code by just-in-time compiler and store it in memory as a cache. I explained earlier that the old compilation method convert all bytecode into native code and store regardless of the usage pattern. It really slows down and update and installation and require more space. But now we have profile guide optimization that selectively creates a native code for the feature frequently used. Profile guide optimization allows the Android runtime to help improve on app's performance by building a profile of app hot code and focusing each optimization. This leads to big improvement while reducing the traditional memory and the storage impact of a fully compiled app. It seemed we found the perfect balance between app speed, storage usage, and update time. However, unfortunately, this method turned out to bring another problem. So what is the problem here? However, app runs slowly at first launch because profile guide optimization rely on device to optimize the app based on this code profile in idle time, which means it could be a few days before the app to run faster. To solve the problem of slow execution at first launch of app, Google introduced the cloud-based profile technique in Android 9. As shown in figure, the profile information of app created on each user's device is uploaded to the cloud server. In the cloud server, most apps share a good amount of code profile information that are used across different users and device, and these can be globally optimized for everyone. The initial user's device can create a profile information for rest of the user space. So the following users can optimize the app after Aot compilation using cloud-based profile data at the time of app installation. This slide shows the whole process of how apps are compiled and executed in Android 10. First, when you try to install the app, APK file is downloaded to your mobile device along with the optimized profile data as described earlier. During the installation, the profile information is used by Aot compiler to selectively compile the bytecode into Aot code for the function that are commonly used by user. Second, when you execute the app, ART checked whether the code of the running method is compiled or not. If the code is already compiled by JIT or AOT, it directly calls the code loaded in memory and executes it immediately. If this code is still bytecode, the interpreter executes it and increases the method execution counter. If the counter of the method continue to increase and it become warm state, the profile information such as a number of method execution is saved in the device as a file. While you are not using the phone but just charging overnight, the service compiled the warm method using the Aot compiler and save it in file as a Aot code. Next time the method will be executed right away as Aot code from the beginning. And if the counter keeps increasing and it finally becomes the hot state, the method is compiled in real time by just-in-time compiler and store it the memory as a code cache. Then the code loaded in memory is executed and as soon as function is called. As you see here, ART has various state of code and complex structure where the apps are optimized and executed based on the pattern of individual and entire user base. Okay, now I'd like to take a closer look at the Android runtime at code level. Based on that, I'm going to propose a technique to analyze the execution of app through the ART customization. As we saw earlier, there are three types of code in ART. The basic text bytecode, compiled Aot code, and JIT code. Aot code and bytecode are saved in file, while JIT code exists in memory as cache code. In mobile device, there are three files in application directory that store the Aot code and bytecode information. The first one is base ART. The file contains ART internal representation of some strings and classes list in the APK, used to boost application startup. The second one is base ODEX file. The file contains Aot compile code for method in APK. The rest one is base VDEX file. This file contains VDEX code of APK with some additional metadata to speed up the verification. These files can be dumped to DEX bytecode and AOT code using the OAT dump module. This picture shows the result of dumping the base ODEX file stored in the application directory. If we look at the first line in blue, there is an init function as a first method in the class, and the name is com_apply internal AC. This init function exists in two different forms. The part written as a DEX code is a bytecode of init function. The second part written as code is compiled code, which was converted from bytecode by Aot compiler. And if we look at the other part, you can see init function in class com_apply internal $1. This function has DEX code, but the code area just shows no code. It is no compiled code, but it exists only as a bytecode. So what does this mean? Even if the function is converted and saved into the compiled code by Aot compiler, the bytecode is saved anyway. This is because the original bytecode is used when the debugging is required or ART is updated to re-optimize the code in the app. If so, let's take a look at how bytecode and Aot code are loaded into memory by ART. Each code is linked to ART method object through the class linker. The ART method object is an instantiated object in the form of C++ class to execute each method within the Java class on ART. Base ODEX file contains the OAT code and the base VDEX file contains the bytecode. When the app is executed, each file is loaded into memory by runtime. This is a simplified picture of how OAT and bytecode are linked to the ART method object inside the ART through the class linker. Before the execution, all methods in the app are linked to the execution code as ART method object. The class linker called the function set entry point from key compiled code to assign the address of Aot code to entry point from key compiled code variable of ART method object. And by calling set declaring class function, DEX cache is assigned to the declaring class variable of ART method object. Now we can call the bytecode through the DEX cache. In short, all functions executed by ART are loaded into each ART method object. We can execute any function through this object. As we saw here, there is more than one type of code we want to execute. So we need to call different type of code for bytecode and compiled code. As shown in the picture, one main function consists of several sub-functions, and each sub-function also consists of several small sub-functions. Let's take a look at the step of call and execute the sub-function 232. Main function, sub-function 2, sub-function 23, sub-function 232 are called in order that each function exists partially as a bytecode and partially as compiled code. Because of that, we need to call compiled code from bytecode and bytecode from compiled code. This cross-call from different code make ART structure more complicated. So let's see how ART cross-call the different code. The first code execution is start from ART method. This is because the ART method object has both bytecode and compiled code. If the function exists as a compiled code, ART method directly invoke the code and execute it. If the compiled code doesn't exist, the interpreter is used to execute the bytecode of function. And after execution of different type of function, the compiled code call the interpreter or vice versa. Sometimes the interpreter call the interpreter again. In this way, state change occur frequently within the ART structure. This is a code flow that analyzes the execution process in ART. Here, compile code called the bytecode and bytecode called the compiled code, and bytecode also called the bytecode. I think it may not be easy to understand the whole process at once, but if we focus on the code execution aspect, there are two parts in whole picture where code is executed. The first part is compiled code, which call ART quick invoke stop function through the invoke function in ART method. This function invoke and execute the compiled code. The second part is bytecode, which call execute mtrp-impl or execute switch impl function through the interpreter execution function. This function converts to bytecode into native code and execute it. All the information required to execute the app go through these two parts. The information contains parameter and return value, the code, call step, and so on. In other words, if we watch the ART method invoke and interpreter execute function, you can trace all code running on Android. Is it really possible? However, there was one missing piece that we could not see in the flow. What is that? That is the process by which compile code called the compiled code. So why is this code not shown in this picture? I'd like to go back and remind you how compiled code is called. As I explained before, ART method invoke call ART quick invoke sub function to execute the compiled code by invoke the code loaded in memory. Let's dig into more about this part. The invoke function of the ART method class called the ART quick invoke sub function. The ART quick invoke sub function is written in ARM assembly code to boost the execution speed. This function has address of target function to be invoked and executed. This picture shows the code to get the address of the function to be executed. This part contains the address of the variable entry point from quick compiled code, and this variable contains the address of compiled code for executing function. Put this address into X9 and directly call the compiled code using branch instruction. Let's call this compiled code A. Then A directly call the address of next function B, which is in compiled code. Again, B directly call the address of the next function C, which also exists on compiled code. Unlike a call structure we saw before, you can see the direct call from memory to memory when compiled code called another compiled code. If this is the case, it's impossible to trace the code when compiled code is executed from compiled code. In addition, since compiled code has been optimized a lot compared to existing Java code, it's tricky to extract the original code even if you access the compiled code. So what I did is to change the call structure so the bytecode always call the instead compiled code for the target function. So I changed the ALT method invoke function to stop executing compiled code, and instead use interpreter to execute bytecode. In this method, the ALT method invoke function to execute the compiled code in the exist flow is not called. Instead, it forced to always call bytecode using the interpreter. This allows you to trace the flow or function because they are executed using the interpreter. Furthermore, you can get original code more easily because execution code you are getting is smart code format. For this purpose, I customized ALT to display all information by adding a trace feature to two functions, ALT method invoke and interpreter execute. As shown here, no matter whether there is a compiled code for the function to be executed in ALT method, it will eventually call bytecode. This figure is a table comparing the stack trace before and after the core flow change in ALT with the technique introduced in this speaking. This figure is divided into two results. The above is the stack trace result before changing the core structure, and the bottom is the result of stack trace after the change. Before the change, function that exists as a compiled code were called from function that exists as a compiled code. In this case, this chapter introduced a framework developed with the previously described technique. As I shown you earlier, the code has been added to the customized ALT to give you trace log. Since the function running in ALT generated huge data, I needed a way to filter out of data for effective analysis. So I add a configuration file to specify the information that I want to trace from ALT. This shows the structure of the configuration file. The first part is to set the UID for your analysis. You need to specify the UID of application you want to analyze here. Second, there is an option to output basic information of the function to be traced. If it is set to Y, it displays the information of the target function, such as argument, return value, and field. Third, this is an option to display the core stack information of the function to be traced. If it is set to Y, it shows you core stack information of the target function. The display code dump option toggles the output of the code from the function you trace. If you set it to Y, then the smart code is printed for the target function. Lastly, there are two options, include and exclude. If we want to track a sufficient function, put the name here in include. Then all functions that contain the string will be displayed. And if we want to remove some unnecessary function from the output, specify the keyword in exclude, then matching the function, function will not be printed. Okay, Walter, please start demo. Right is the Ubuntu console screen, and the left is phone mirroring screen. The app to be analyzed is Santander used in Argentina. First, open the configuration file on my mobile device. As explained in previous chapter, here is a target app UID, stack trace option, code dump option, and so on. First, we get the UID of target app. UID is 10.16.8. If you written hash 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 in front of it 3 times, the option does not work. Okay, start app. First, we get the you can see all the function executed in ART. Too many functions are executed. You cannot you can save it as a log and analyze it later. You can see all functions executed in ART. There are so many functions. Second, we will add an option to remove the default Android function. You will only see the custom function. So I excluded the Android default function and start it again. The amount of function displayed is much smaller than before. And I try to choose a few of functions that you want to analyze in detail. First, I select com Indra function. You only need to insert a partial string of the function name to be analyzed. Second function, AR com Santander function. copy and paste. And I search other function. I find the com fryer function and copy and paste to. Choose a few of functions that you want to analyze in detail. And I try to run the app again. You can only check the execution of the target function. Then I try to set the ARG option to Y. Now you can see the argument and the return value. Number 1 and 2 are first and second parameter, and R is the return value. You can see all the information. You can see all important information really easily. Let's take a closer look at the encrypt function. Copy the encrypt function. I target the encrypt function. Let's take a closer look at the encrypt function. Then set the code dump option Y. Set the code dump function to Y. You can see smiley code of target function method. You can see smiley code of target method in real time. Then I try to set the stack trace option to Y. I start the app. Now you can see stack trace of target method in real time. Okay, Walter, please finish the demo, please. Thank you. In conclusion, I developed a new analysis environment by analyzing and modifying the structure of ALT. This method is very easy and effective and powerful. Thank you for listening. If you have any question, please contact us on Twitter. Thank you.